Today I wanted to lecture about something known as the Master Theorem. And the Master Theorem combines two topics that we've already studied. It combines recurrences and it combines big O notation. What it does is it takes a recurrence of a very general form and it shows you how to get a big O estimate on the growth of that function defined by the recurrence. So, for example, here's the statement of the theorem. Let's assume that you have a function f of n and it equals a times f of n over b plus c times n to the d. Okay, and these a, b, c, and d numbers you want to think of as constants. Okay, so a is greater than or equal to 1, b is an integer greater than or equal to 1, and c and d don't have to be integers, but they both have to be positive and non-negative. And we're also going to assume that n here is divisible by b. Okay, so notice this is a recurrence. It is not a homogeneous linear recurrence. We have this term sitting over here that doesn't make it homogeneous. But it still is a recurrence, and we don't know how to solve them exactly. But what the Master Theorem tells you is that you can get a big O estimate for what this function is. Okay, so if you have a recurrence of this form, the Master Theorem says the following. If a is less than b to the d, then f of n is big O of n to the d. Okay, this is case 1. Case 2 is if a equals b to the d, then f of n is big O of n to the d log n. So this is case 2, this is case 1, and case 3 is if a is greater than b to the d, then f is big O of n to the log base b of a. So this looks a little bit complicated, but it's really mechanical. We're not going to prove the theorem, but I want you to use it as sort of a mechanical tool. So if you're given a function of this particular form, you determine whether you're in case, based on what a, b, c, and d are, you determine if you're in case 1, if you're in case 2, or if you're in case 3, and you solve those cases appropriately. So for example, let's do an example. Let's assume that we have a recurrence, f of n is equal to 2 times f of n over 2 plus 3. Okay. Now remember, we wanted f of n, we're looking for f of n of the form a times f of n over b plus c times n to the d. So a in this case is equal to 2, b in this case is equal to 2. Because we have a plus 3 here, you don't see an n to the d. This is plus 3 times 1. That means that d is 0 and c is 3. Now we need to check our three cases and see which case we're in. So case 1 is a is less than b to the d. Are we in this case? Well, here a is 2, b is 2, and d is 0. So is 2 less than 1? No. So we're not in case 1. Case 2 is a equals b to the d. Again, a is 2, b is 2, d is 0. Does 2 equal 1? No. What is case 3? Case 3 says a is greater than b to the d. So here we have, again, a is 2, b to the d is 1. Bingo, we're in case 3. And case 3 says that f is big O of n to the log base b of a. What is log base b of a? It's log base 2 of 2, which is 1. That implies that f is order n. So again, I took this recurrence, f of n equals 2 times f of n over 2 plus 3. We figured out what a, b, c, and d were. We then figured out what case we're in, and we realized we were in case 3, so we said that f is big O of n to the log base b of a. B and a were both 2. That implies that f is big O of n. Let me just go back to the Master Theorem and remind you what it says, in case you want to write this down or pause. It says if you have a recurrence of this form, you check which case you're in, and you output whatever your big O estimate is of f.